Across the vast cosmos, the question lingers, are we truly alone? Scientists are exploring the universe, from our solar system's icy moons to distant exoplanets, seeking environments where life might exist. Join us as we delve into the fascinating science behind the search for life beyond Earth. And here are our two hosts deep diving into this topic.
It's something we all do, right? I mean, looking up at the night sky and kind of like wondering, are we alone?
Oh, yeah, that's like a fundamental human question.
It is. It is. It just sparks your imagination, doesn't it?
Totally.
So today on the Deep Dive, we're tackling that question. What does science actually tell us about the chances of life existing beyond Earth?
And the cool thing is, the more we dig into the scientific research, the more interesting it gets.
Exactly.
Okay.
Exactly. So we've got a ton of great material here that dives into, like, all the current scientific thinking about life in the cosmos, basically. So our mission today is to pull out the most important bits, like the real nuggets of knowledge about finding life out there. We'll be looking at everything from, like, how do we even define life?
Right.
To these mind-boggling, like, habitable zones.
Yeah.
To the incredible adaptability of life on Earth.
Yeah.
So if you've ever felt kind of overwhelmed by this topic, like, where do you even begin?
Right.
Don't worry, we're going to guide you through it. So, like, okay, let's just jump right in.
Okay.
It seems like the first hurdle is, like, how do we even define what we're looking for? What actually counts as life?
Right. You'd think we'd have that figured out, but when you try to pin it down, it gets tricky pretty quickly.
I know.
And believe it or not, there are over 100 different definitions of life that have been documented.
Wow, over 100.
I know. It really highlights that life isn't just a thing. It's more like a process characterized by change and the ability to change.
Right.
And we've only got one example to work with,
Yeah.
Life on Earth. So it makes it tough to know if our definitions are broad enough.
That's right. So what are, like, some of the main ways that scientists are trying to define this whole thing, this process we call life?
Okay, so there are a few main perspectives. There's the metabolic definition, which views life as, like, these bounded systems that exchange materials with their environment without fundamentally changing themselves over time. So, like, always adapting, but never really changing at their core.
Right, I gotcha, okay.
Then there's the physiological definition, which looks at what a system actually does.
Okay.
So things like, taking in nutrients, growing, reproducing, responding to stuff in its environment.
Okay.
Then there's the biochemical definition, which focuses on, like, the molecular machinery, the nuts and bolts.
Right.
So we're talking DNA, the stuff that carries genetic information.
Okay.
And enzymes, those things that make biochemical reactions happen.
Right.
And then even physics has a perspective.
Wow.
They define life as an organized thermodynamic system that can reproduce and evolve.
Wow, okay.
So it's getting pretty deep.
It is. So it's a lot more than just breathing and eating then.
Yeah, exactly. I mean, life on Earth gives us a great starting point, right?
Yeah.
We see all these characteristics: responsiveness, growth, metabolism, energy transformation, reproduction, homeostasis, organization, adaptation, response to stimuli.
Right.
And then there are those underlying principles.
Like, being organic, largely carbon-based, maintaining low entropy, having some kind of genetic program, interacting with the environment, adapting to it, reproducing and evolving.
Okay.
But at its core, it's all about chemical transformations. Directed by these inherited catalysts, passing information down through molecules.
Okay.
It's like a chain reaction of complexity.
I like that. A chain reaction of complexity. Yeah. Okay, so NASA has that definition too, right? It's a self-sustaining chemical system capable of Darwinian evolution.
Yes, exactly.
Okay.
That one captures a lot of the key things.
Right.
Metabolism, that's the self-sustaining chemical system.
All right.
Cart reproduction.
Right.
Because you need that for evolution.
Right.
And the ability to change over time, to adapt.
Okay.
But it's not perfect. Right.
Right.
Some people point out that a single individual reproducing sexually might not fit that definition.
Okay.
Because evolution happens at the population level.
Right. Okay.
And there's another...
NASA's definition leans pretty heavily on what we know about life on Earth.
Okay.
Carbon-based, the role of water, all that.
Right. Which brings us to the really mind-blowing part.
Right.
The possibility of life that isn't built on carbon or water.
Yeah.
Carbon just seems so fundamental,
It does, doesn't it?
It does, yeah.
I mean, carbon's ability to form those 4 stable bonds is amazing.
Right.
That's what lets it create these long chains, these complex molecules that are the building blocks of life as we know it.
Yeah, okay.
But we have to be open to the possibility that under different conditions, other elements could step in.
Okay.
Silicon, for example.
Yep.
It's right below carbon on the periodic table.
Okay.
It shares some similar properties.
Right.
So some scientists have theorized that it could be a basis for life.
Okay, but our material points out some serious challenges for silicon-based life, though, right?
Yeah, there are definitely some hurdles. I mean, silicon atoms are bigger than carbon atoms,
Okay.
which makes it harder for them to form double or triple bonds.
Right.
Those are really important for biochemical processes here on Earth.
Right.
Plus, silicon-based molecules like synlanes, they tend to be less stable.
Right.
They react more easily with water than their carbon counterparts.
Okay.
Silicon polymers are pretty stable, I'll give them that.
Yeah.
But they're still not as versatile as carbon-based polymers.
Okay, so not a perfect substitute?
Not quite, and there's one more thing.
What's that?
Silicon's actually less abundant in the universe than carbon.
Ah, okay, so even if it could work, it might not be as likely.
Exactly.
Okay, so what about other elements? I mean, are there any other contenders out there?
A few have been suggested. Boron, phosphorus, but they're not as versatile.
Okay, so carbon is still king, at least for now.
For now.
Okay, so what about water? I mean, it's so essential for us.
I know, it's hard to even imagine life without it.
It is, yeah. So could there be life that doesn't need water?
It's possible. Again, we have to think outside our Earth-centric box, right? Maybe in colder environments, other solvents could work. Ammonia, for example.
Okay.
Pretty abundant in the universe.
Right.
Shares some key properties with water.
Okay.
It's polar, can dissolve organic molecules,
Right.
but its hydrogen bonds are weaker than water's.
Okay.
And it's got a much lower temperature range for its liquid state.
So it's got to be pretty chilly for ammonia to work.
Yeah, pretty much.
Okay, what about other options?
Well, methane is interesting.
Okay, why is that?
It's abundant, like ammonia,
Right.
and it exists in liquid form on Titan, Saturn's moon.
Right, okay.
It's nonpolar and a weaker solvent than water.
Okay.
But it could potentially support life with a completely different biochemistry.
Okay, so methane-based life could be a thing.
It's on the table.
Wow, okay. Anything else?
There's been some mention of hydrogen fluoride and hydrogen sulfide,
Okay.
but they've got their own limitations.
Right, right.
So still a lot of unknowns there.
Yeah, it sounds like it.
But the point is, we can't rule anything out.
Okay, so we could be looking for life that uses totally different building blocks than we do.
Exactly. And it gets even wilder.
How so?
Think about the biomolecules themselves.
Okay.
Earth life uses L-form amino acids and D-form sugars.
Right.
But life elsewhere could use the opposite forms.
Wow, okay.
Scientists have even come up with these things called xenonucleic acids, or XNAs.
XNAs?
They have different sugar backbones that could store genetic information.
So basically, a different way of carrying the blueprints for life.
Yeah, something like that.
Wow, that's amazing.
Mm.
Okay, what about even more radical ideas?
Okay, now we're getting into some really speculative territory.
I'm ready, I'm ready.
Okay, some people have even proposed things like heteropoly acids or boranes,
Okay.
but those are pretty theoretical at this point.
Right, right. Okay, so this is really blowing my mind.
Yeah.
The material even talks about life existing outside of planets, which sounds pretty far out there.
I know it does, but we have to consider all the possibilities.
Right?
For example, in 2007, some researchers put forward this idea that dust particles in space, under certain conditions in plasmas,
Right.
they could act in ways that resemble life.
Wow, okay.
Another hypothesis involves these theoretical things called magnetic semipoles.
Magnetic semipoles.
They're connected by these things called cosmic strings.
Okay.
And some scientists think they might go through a form of evolution inside stars.
Okay.
And then there's the really out there idea of non-corporeal consciousness, like existing as energy patterns in stars or gas clouds.
So basically like a thinking star or a thinking cloud of gas.
Yeah, something like that. I mean, it's really stretching the definition of life as we know it.
It is, but it's fascinating to think about.
Yeah, totally.
So the bottom line here is that we just don't have one clear definition of life.
Right.
And the universe is massive.
It's beyond massive.
So we have to keep an open mind.
Absolutely.
We can't limit ourselves to just looking for carbon-based things swimming around in water.
Right. We're probably missing a lot if we do that.
Exactly. We're influenced by the one example we have, life on Earth. But the universe is way more diverse than that.
Yeah, it's gotta be.
Okay, so we've wrestled with this whole definition of life thing.
We've given it a good shot.
We have. So let's move on to what we think are the essential ingredients for life based on what we know about Earth.
Okay, sounds good.
What's the recipe, so to speak?
All right, well, based on what we see here on Earth, there are a few things that always seem to pop up.
Okay.
Liquid water, a suitable atmosphere, a source of energy, and those biogenic elements. Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur.
Right.
CHNOPS for short.
CHNOPS.
Yeah.
I like it. Easy to remember. Okay, so liquid water is always at the top of the list when we talk about habitable planets.
Yeah, pretty much.
Wow.
Why is it so important?
Well, it's a fantastic solvent. It lets all that complex chemistry happen, dissolves substances, facilitates biochemical reactions inside cells, and it's vital for transport, moving chemicals around within organisms.
It's involved in metabolism, getting rid of waste products.
Right.
It's polar, which makes it this amazingly versatile solvent.
Right.
And it makes up a big chunk of the mass of most living things on Earth.
Right.
And on top of all that, it's got these unique properties that are just perfect for life.
Like what?
Like it can regulate temperature, transport nutrients really efficiently.
Oh, okay.
And ice is less dense than liquid water.
Which is pretty unusual, right?
It is. And it's super important for life,
Right.
It helps support ecosystems.
Okay, so it's not just about water being there. It's about all these special properties it has.
Yeah, exactly. But we have to remember our understanding is based on Earth. So
Right.
we can't rule out the possibility of life using other solvents.
Right. We talked about that earlier.
Exactly. But for now, when we're searching for life out there, liquid water is a key indicator.
Okay, makes sense. So what about a suitable atmosphere?
Yeah, atmospheres are pretty important too.
Okay, how so?
Well, for one, they act as a shield. They protect the surface from harmful solar radiation.
Right.
And they help keep the temperature stable through the greenhouse effect.
Right.
Which is controlled by certain gases in the atmosphere.
Okay.
And then for more complex life like us, oxygen is essential.
Right.
While plants need carbon dioxide for photosynthesis.
Right.
And nitrogen is super important too.
Okay, why is that?
It's a key part of DNA and RNA.
Okay.
And some bacteria can even convert atmospheric nitrogen into forms that other organisms can use.
Wow, I didn't know that.
Yeah, it's called nitrogen fixation.
Okay, interesting.
And of course, you need enough atmospheric pressure to keep water liquid on the surface.
Right.
So it's all about a balance, really.
It is.
Okay.
Okay, so what about energy? I mean, here on Earth, the sun is the main source, right?
Yeah, the sun powers most life on Earth.
Right.
Plants use sunlight for photosynthesis, which is the basis of almost all food chains.
Right.
But energy can also come from chemical reactions.
Yeah, like what?
Redox reactions, for example. Those can be powered by geothermal processes or even starlight.
Wow, so even starlight can provide energy.
Yeah, in some cases.
That's amazing. Okay, so what about geothermal energy? Where does that come from?
A planet's internal heat.
Okay.
It can be from when the planet formed, radioactive decay in the core, or even tidal forces from a nearby moon or star.
Right.
It's pretty amazing, actually.
It is, yeah.
Yeah.
And are there any organisms that don't rely on sunlight at all?
Yes, there are. They're called chematotrophs.
Okay.
They get their energy by oxidizing inorganic materials.
Like rocks and stuff.
Yeah, things like that.
Okay, so they're not relying on the sun's energy at all.
Nope. They've found a different way to power themselves.
That's incredible. And what about the amount of light? I mean, does it have to be as bright as it is here on Earth?
Not necessarily.
Yeah.
Even out at Pluto, there's enough light for some types of photosynthesis.
Really? That far out?
Yeah, it's pretty amazing.
It is. So light might not be as limiting as we thought?
Ex-
Okay, so there are a lot of possibilities for life to get the energy it needs.
Yeah, it's more diverse than we might initially think.
Yeah, okay. What about other essential elements? You mentioned CHNOPS earlier.
Yeah, so besides carbon and hydrogen, which is part of water,
Right.
we've got nitrogen, phosphorus, sulfur, and then a bunch of other trace elements.
Oh.
They're all crucial for building complex biomolecules and making all those biochemical processes happen.
Right.
But again, life elsewhere might not use the same elements that we do.
Right. We've got to keep an open mind about that.
Always.
The material we're looking at has this table 1, that summarizes these requirements and how common they might be in our solar system.
Oh, yeah, that's a good one.
Yeah. What are some of the key takeaways there?
So the table shows that energy in various forms seems to be pretty common throughout the solar system.
Okay.
Light energy, chemical energy, it's all out there.
Right.
Carbon's pretty widespread too, mainly as carbon dioxide and methane.
Okay.
But readily available liquid water, that's actually pretty rare.
Right. I guess we're pretty lucky here on Earth.
Yeah, it seems that way.
Okay.
Nitrogen is probably common as well.
Okay.
And while oxygen isn't so common in its free form,
Right.
if we find a lot of it on an exoplanet, that could be a sign of oxygenic photosynthesis, which would be a big deal.
Yeah, that would be a strong hint that there's life there.
Exactly.
Okay, so the table also talks about temperature and pressure conditions for liquid water, which are pretty limited in our solar system.
Yeah, but here's the thing.
Yeah.
Even small amounts of moisture might be enough for some microbial life.
Okay.
And a lot of microorganisms can tolerate a lot of ultraviolet and ionizing radiation.
Okay.
So radiation might not be as big of a problem for life as we thought.
Interesting. So it's more than just having the right ingredients. It's about how they all work together.
Yeah, it's like a complex recipe. You
Right,
know, you
yeah.
need the right amounts of everything and they all have to interact in the right way.
Yeah, that makes sense. Okay, so this leads us to the idea of Goldilocks zones.
Yes, the Goldilocks zones.
These regions around stars where planets might be just right for life.
Just right. Not too hot, not too cold.
Exactly.
Right.
So how do we define these zones?
Well, technically it's called the circumstellar habitable zone,
But-
or the Goldilocks zone, as you said.
Right.
And it's basically the range of distances from a star where a planet with the right atmospheric pressure could have liquid water on its surface.
Okay.
Not so hot that the water boils away, not so cold that it freezes solid.
So just right for those Goldilocks conditions.
Yeah, exactly.
Okay, so what determines where this zone is around a particular star?
Mainly the star's luminosity.
Luminosity. Okay.
That's how much light and heat it gives off.
Right.
And that's determined by the star's size, mass, and temperature.
Okay.
So hotter, more massive stars, they put out a lot more energy.
Right.
So their habitable zones are wider and farther out.
Okay.
Cooler, less massive stars like red dwarfs.
Okay.
They have narrower habitable zones that are closer in.
Right, because they're not putting out as much heat.
Exactly.
So red dwarfs are actually the most common type of star in our galaxy.
They are.
But they present a bit of a problem, don't they?
Yeah, they do.
What is it?
Well, planets in their habitable zones get hit with a lot of X-ray and ultraviolet radiation,
Okay.
which could be bad for life as we know it.
Right, right.
It's not ideal.
No, it's not.
Yeah.
So what about other types of stars? Are there any that might be better for life?
Some astrobiologists think that orange dwarfs might be good candidates.
Orange dwarfs. Okay.
They're a bit cooler and less luminous than our sun,
Okay.
but they burn steadily for a really long time.
So they could provide a more stable environment for life to evolve.
Yeah, potentially.
Okay, so it's not just about surface temperature and liquid water, though, right? I mean, a
Right.
planet could have underground oceans
Yeah,
or a
totally.
really thick atmosphere that affects the surface temperature.
Exactly. So while the traditional idea of the habitable zone focuses on surface water,
Right.
there are other ways a place could be habitable.
Right.
The atmosphere plays a big role.
Okay, how so?
Well, the presence and composition of the atmosphere can affect things,
Okay.
like greenhouse gases, reflectivity, and circulation patterns.
Right.
And those can all impact surface temperature.
So a planet could be outside the traditional habitable zone, but still have liquid water if it has the right kind of atmosphere.
Exactly.
Okay, that's pretty cool.
Yeah, and then there are internal energy sources, too.
Like what?
Radioactive decay in the core,
Okay.
tidal heating from a moon or the host star.
Right.
Those can keep water liquid even on planets far from the habitable zone,
Okay.
like Europa, for example.
Right, with its underground ocean.
Exactly.
Okay.
And then there's the idea of a continuously habitable zone.
Okay, what's that?
That's the region where liquid water could have existed for a very long time.
So plenty of time for life to evolve.
Exactly.
Okay, and then there's also a galactic habitable zone, right? Which takes into account things like radiation levels and star density.
Yes, so it's not just about the star system, it's about the galaxy as a whole.
It's like there are habitable zones within habitable zones.
Kind of, yeah.
Wow, it's pretty amazing. So what are the current estimates for habitable planets in the Milky Way?
Well, the Kepler mission really changed our understanding of that.
Right.
In 2013, based on Kepler data, astronomers estimated there could be as many as 40 billion Earth-sized planets in habitable zones.
40 billion, wow.
Yeah, a lot.
That's incredible. And how many of those would be around sun-like stars?
They estimated about 11 billion.
Wow, so even just around stars like our own sun, there could be billions of planets that could potentially support life.
Yeah, it's pretty mind-blowing.
It is, it is. And have there been other estimates since then?
Yeah, some have suggested even more, like 20 billion or even the 60 billion.
Wow.
But a more conservative estimate from 2015 put the number at around 300 million around sun-like stars.
Okay, so even the conservative estimate is still a huge number.
Oh, yeah, definitely.
And then there was a study in 2020 that said maybe half of sun-like stars could have rocky, habitable planets.
Yeah, so the numbers are still being refined.
Right, but it seems like there are a lot of potentially habitable planets out there.
Yeah, it's safe to say that.
And what about estimates from before Kepler?
Well, there was one from way back in 1964 that suggested around 600 million.
Okay, so even before we had all this data from Kepler, people were already thinking that habitable planets might be common.
Yeah, they had a hunch.
So what was Kepler's main conclusion about all of this?
They concluded that somewhere between 20 and 50% of the stars we see could have small, rocky planets in their habitable zones.
Wow. So when we look up in the night sky, it's possible that a good chunk of those stars have planets that could be like Earth.
Yeah, it's a pretty amazing thought.
It is. And if we extrapolate that out to the whole universe with all its galaxies.
Oh man, then the numbers get really crazy.
I bet.
Some researchers have estimated there could be 56 sextillion habitable planets.
56 sextillion, that's just an unfathomable number.
I know, it's hard to even wrap your head around it.
It is. So it seems like the potential for life out there is just enormous.
Absolutely. The numbers suggest that it's highly likely that life exists elsewhere.
And the Kepler mission was specifically designed to find these planets, wasn't it?
Yeah, it was our first real planet hunter.
Okay, so how did it work?
Well, it launched in 2009.
Okay.
And it basically stared at one patch of the Milky Way,
Okay.
looking for tiny dips in a star's brightness,
Okay.
which happens when a planet passes in front of it.
Right, that's called a transit, right?
Exactly.
Okay.
And even though it had some technical problems later on,
Right.
they were able to repurpose it for the K2 mission.
Okay.
And it kept making observations until 2018.
Okay.
By the end, it had confirmed over 2,600 exoplanets.
Wow. That's a lot.
And it gave us strong evidence that billions more are out there.
Okay, so Kepler really revolutionized our understanding of exoplanets.
Totally.
So it seems like liquid water, which we think is essential for life, might be pretty common in the universe.
Yeah, and that definitely increases the chances of finding life out there.
Okay, now, even if a planet is in a habitable zone, the conditions on the surface might still be pretty extreme.
Oh, yeah, definitely.
But that's where extremophiles come in, right?
Exactly.
These are the organisms that can survive in what we would consider really harsh environments.
Yeah, they're amazing.
They are. They are. And their discovery has really changed how we think about life beyond Earth, hasn't it?
Totally. It's shown us that life can exist in places we never thought possible.
Yeah. So where have we found extremophiles here on Earth?
Oh, all over the place.
Okay, like where?
The deepest parts of the Earth's crust, hydrothermal vents,
Okay.
frozen seawater, acidic or alkaline environments, places with tons of salt,
Okay.
high radiation levels, really dry places, even inside rocks.
Inside rocks, wow.
Yeah, they're called endoliths.
Endoliths, okay. I'm learning so much today.
It's a whole new world down there.
It is. It is. So what are some of the different types of extremophiles?
Well, we've got thermophiles and hyperthermophiles. Oh,
They love hot and very hot temperatures, respectively.
okay, makes sense.
Psychrophiles are the opposite. They thrive in the cold.
Right.
Acidophiles and alkalophiles like acidic and alkaline environments.
Okay.
Halophiles need lots of salt.
Right.
Barophiles, also known as pisophiles, can handle immense pressure.
Okay.
Radio-resistant organisms can take high levels of radiation.
Right.
Xerophiles can survive in very dry places.
Okay.
And then we have the polyextremophiles.
Okay, what are those?
They're the ultimate survivors.
Okay.
They can tolerate multiple extreme conditions at once.
So like super extremophiles.
Yeah, you could say that.
Okay, cool. And what are some examples of polyextremophiles?
The most famous ones are probably tardigrades.
Tardigrades, okay.
They're also called water bears.
Water bears, that's cute.
I know, right? But they're incredibly tough.
They are, yeah. So are all extremophiles just single-celled organisms?
Mostly, yeah. Bacteria, archaea, other microorganisms.
Okay.
But there's some eukaryotes, too. Eukaryotes, remind me what those are again.
They're organisms with more complex cells.
Okay.
Like fungi, protists, even some multicellular creatures.
Wow, so even some more complex life forms can handle extreme conditions.
Yeah, it shows how adaptable life can be.
It really does. So how does all this relate to our search for life beyond Earth?
Well, extremophiles show us that life can exist in a much wider range of environments than we thought.
Okay.
They're like models for the kind of life we might find on other planets and moons.
Okay, so they're giving us clues about where to look and what to look for.
Exactly. Like, psychrophiles suggest that life could exist in the icy oceans of places like Europa.
Right.
Thermophiles and hyperthermophiles point towards life in hydrothermal vents,
Okay.
which could be on Europa or Enceladus.
Okay.
Halophiles make us think about life on places with lots of salt, like Mars.
Right.
Acidophiles hint at life in the acidic clouds of Venus.
Okay.
And endoliths, those are the ones that live in rocks that could be on Mars too, hiding underground.
Wow, so extremophiles are really expanding our view of where life might exist.
They are. And they're also giving us clues about what that life might look like.
Okay, how so?
Well, the way they've adapted to survive in these harsh conditions is pretty amazing.
Yeah.
They have special enzymes, unique metabolic pathways, protective structures, and that tells us what kind of biosignatures or signs of life we should be looking for on other planets.
So we're using what we've learned from extremophiles to guide our search for extraterrestrial life.
Exactly.
That's pretty cool. And the material mentions that this is even influencing how we design our space missions.